Oh, that's all right. I'll fix that. I have to download all the Zoom things and put them on YouTube. It takes a while, but hide the meeting control. That's good. And no one's there, so I don't know if they can hear, but they can probably hear. Anyway, what the homework, let me look this up. The homework, yeah, it's not easy. Kind of went through this, right?
The question was asking for the derivation.
Yeah. Yeah, it's asking for the derivation. Like where does that thing come from? So he's got I think what page it's on. It's somewhere. It says on the question, right? 6281. Right here. So it's kind of like, isn't it right here, right here? So this, so W is this energy. W is a viral, right? Because the internal viral, and W, small w is this energy thing. So it's like the derivative of the energy with respect to distance is the force. Force times distance is energy. So it's like you have all the particles and they're separated by some distance. There's a force between them. So there's a fit force. U is that like a 612 potential, and the x-axis is R, and like you're somewhere on R, so you get like a potential there. You get a force there. Derivative of that energy there is a force. If you multiply that force by the distance between the two particles, you get the energy that's pulling the particles. Right. So this little w is the energy that's pulling the particles. You know, sum over all the energies to get this W, and then it's divided by the V, which he doesn't say what it is, but it's a volume. I think it's a volume of one bead or something. Right. So where does it's like an integral of energy, right? That's kind of what you're looking at. So so you got this second viral coefficient thing. Integral of energy. So these are all the kind of not all the different ways. There's other ways to look at the viral coefficient, believe it or not. But
like that one is
yeah, this is like an energy. Like this phi is an energy. Intermolecular pair potentials and energy between the pairs, kind of like the same thing, this small w, kind of, right? So, hey, Kyle, can you hear me? Kyle Rojek, can you hear me? Unmute. Can you hear? He's not responding.
Yeah, I can hear you, Professor.
Thanks. I just, like the last time, time before, it didn't work, you know, so thanks. So this exponential, you can, if the argument to exponential is small, which I don't know if it is or not, but basically if it is, expand this into a power series. So you say 1. So there's a 1 here, so that those two ones cancel. The next argument is the thing. So it's minus this potential. There's a minus here, so those two cancel. The next one would be the square of this thing divided by 2 factorial. And then the next one would be the cube of that divided by 3 factorial, and it keeps going on. So if it's small, the high powers are much smaller than the low powers, so you just keep the first one. So this whole thing just becomes that potential, except the sign changes because there's a sign here. So then this becomes like a sum of the energies, if you look at it that way. So as long as your potential is smaller than KT, then this thing becomes kind of what he's talking about there, like kind of a sum of W's, small W's. And the W's could be calculated that way. So he's doing a simulation. How's he going to calculate that thing? This is kind of how you would calculate that thing. And then the V, I went through in class what the V, how you get the V from this thing. I mean, PV is energy, so you have pressure times volume. So it has to have a V in there if you have W is energy. That's one way to look at it. And then KT is energy and rho is number density. So that is kind of a problem. Number per volume. Now that works out because a volume time, it would have a volume times P gives energy. So number times KT is energy. So energy, energy by volume, and then pi is pressure, which I guess is energy by volume. Right, so the units kind of work out. That's good enough. I mean, I think I said more before, but that's kind of where that's coming from. It's not that easy. Like, it isn't clear. He just bring out, he doesn't give a reference or anything. It's just like, oh, that must be how it is. But it's kind of good to look at it and say, like, what is he talking about? You know, that's the point of that question. Any other things on this? The first one's pretty hard. They're all hard here, so it's going to be, I did go through them though, so he gives it two ways to get the theta point. One is that at the theta point, the chain is Gaussian. If it's a linear chain, it's NL squared, R squared is NL squared. So R goes with N to the 1/2. So nu is 0.5, nu is 1 over df. And if it's a randomly branched chain, I mean, people have done simulations and found out that nu becomes, df becomes 2.5, so nu becomes some weird number, 1 over 2.5. So he says what that is, 2/5 or something. So, and then if you use that as a criteria, then or criterion, then basically you can say when you reach that point. So he uses that 2.5. He says plus R, then nu here is the 5. Nu is 3/5, 1 over 5, 3/2, 5/2, right? 1 over 2/5, whatever. This is, we figured out, was the parameter to get where the critical point 0. And then when that's 0, then this thing should work and everything should be the same. If you divide by molecular weight to that, you should get a constant. So he does that. He uses 2.5 and he finds where this critical lambda is and also where the critical temperature is that way. That's way 1. Way 2 is he does something like that first equation, calculates B, and B2 goes to 0 at the critical point, at the theta temperature. So that's his other way of doing it. He does it both ways, gets the same answer. That's somewhere section C here. This thing is how to do that. So that's this business. There's a lot to it. I mean, if you figure out all that stuff, then you kind of have a pretty good handle on what this zero coefficient thing is and what's going on. I don't know. I'm not going to go through the whole thing. Do you want me to go through the whole thing? All right, then that's that one, right? That's 2 at least. Krieg-Baum gives that, and then he gives some oddball equation that he says is made up. Equation, what page is this? Figure 4, equation 4. Equation 4 is this hyperbolic tangent function. So hyperbolic tangent kind of can look like, let's see, I'm way beyond equation 4. So the question is, he's got exactly the same shape as the Flory-Kriegbaum. I mean, this RG thing is just the same as what we had in class. And it maybe starting with Flory-Kriegbaum and then tweaking it would have made more sense, you know. But all right, it's not Gaussian chain. So where in the Flory-Kriegbaum does let me hide this thing. This guy's beeping. So where in the Flory-Kriegbaum, the first step in Flory-Kriegbaum, before you even get to Flory-Kriegbaum, when you're just at the energy of an isolated chain, which is the first term, is Gaussian. So Flory-Kriegbaum assumes Gaussian because the first step of it is to use a Gaussian chain and then perturb it. This one is decidedly not Gaussian because it's got all these branches in. In fact, he kind of showed that it's 2.5 dimension. So basically the first term won't work. But nonetheless, the shape of the curve he gets is almost exactly the same. And I bet if you could fit this with a Flory-Kriegbaum, the same. So anyway, he uses this function to fit it, which he picks up from somewhere. He didn't invent that function. It came from reference 34 for some kind of brush polymers. So basically just talk about that. So this is, oh, the same guy, same group, Jorge Douglas. Fetters is a guy that invented this. Well, he didn't exactly, he kind of was part of the team that invented this packing factor. And this Kareem is the guy, not sure where he is now. He was at Akron for a while. Oh, and Sukil Saticha is a guy from Argonne National Lab. So anyway, this is kind of an all-star team too, this paper from 1996, a long time ago. But that's got some citation. So it's kind of, anyway, that's where the tan hyperbolic tangent, maybe it has some explanation. I didn't look at that paper. It looks like that paper would be worth looking at. Creek Baum. It's just like critique, like why would you use that equation? I think you probably should try to dig up that paper, 1996. Should be able to get it. So I can try to post it. What reference number? This one, right? It's called Physics B. So the way I get a paper is this, because it used to be easy to get papers and now it's harder. So I go to the library. I guess that, oops, something like that. Two periods. Oops. Go here, then I go to database. This is a long process. It used to be like you could just click or something and get it. Web of Science. You guys might know a faster way to get papers, but this is the way I get them. It's gonna call me. Things are getting more and more. Like, who's gonna steal your? Oh, phone to phone. Let's see. It's not calling me. This is the problem with these things. It's not going to work here for some reason. I have phone message. Yeah, I can't do it because it didn't call me. I don't know. Sometimes it doesn't call. Let me try again. Cancel. Call me. There, it's calling now. All right. Then this, like I said, this is a long process, but it's kind of worth showing you how to do it. So you get to this Web of Science somehow. Then you can just put the title in. So we have access to almost everything, but only if you go the right way to get it. So then here, if you click within that to get full text from publisher, then you can get the paper, So that's the paper, right? It's kind of a tedious process. Yeah, this looks pretty weird. Like, these are the scattering curves. This stuff has structure in it, It's not the same, like a Polymer coil is a featureless curve. This doesn't look particularly appropriate. Like, that, for one thing, it's, he's setting it up for some different system. So why that would work here, it doesn't make any sense. So anyway, what this Web of Science does for you, like the advantage of it, it tells you the number of citations. There's 18 people cited this since 1996. That's like, I don't know how many, 30 years or something. So that's like not a lot. He cited 22 references. If you want to see his references, you can click that. And you can get each paper, you can click it there. That's why it's called a web. So you can go forward or backward. So forward, the future after the paper is like everyone that cited him. So you can find, so you have a web, like a paper, you find a paper is exactly what you want to know about. And you can say, like, all the stuff he cited is a web. And then each of those papers has the same thing. It also has like all the references. So you can see that would multiply pretty quickly. And going forward, it's like everyone that cited that paper, right? And then each of these also has citations, like this paper. Matt Terrell's a guy, he's now at he was at Minnesota, now he's at University of Chicago. He founded the molecular, it's like a biomolecular something, big time money dump place in the University of Chicago for polymers. Anyway, that's got 33 citations, more than the hit squad one. Jorge cited his own paper. That's the paper we're looking at. Then, so you can see, like, kind of everyone that maybe used that function. Mark Dadman is at University of Tennessee chemistry department. He did simulations. He does neutron scattering too. And then Fetters, same guy. And then Satija is a guy at Argonne. And then who else is in here? Sato, name's familiar. I don't remember where. But must be a famous guy. Kent is a guy from Sandia. I shared an office with him. I was a postdoc. And Kent cited this a lot, so he likes this a lot apparently, and he's working with Satija. There you go. So there's more. There's like, oh, page 101. That's all there are for this paper. So anyway, you could look through each of those papers. Oh, Bill Hamilton is at Oak Ridge, and Greg Smith. These are neutron scattering people. Neutron confinement cell for investigating blah blah blah. Somehow they use that function. Anyway, so this if you're searching for literature, it's really helpful because you can go like in both directions, then find all the citations from all those, and then find everything, and then you can find all the papers. If you find a paper that's perfect, then you can find all the papers that have anything to do with it, more or less, right? So it's pretty powerful, and you can tell which ones are good by the number of citations. So it's a pretty good search tool to use. It's on the library, you just sign in. So anyway, yeah, that paper might be worth looking at for that question if you want. Figure 6. This is just a BS question. Why would they use that function? It doesn't make any sense. It's not even close to the right one. Blah 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 blah. Right? He doesn't even have chi in that function. Right? So what's the point of it? You can critique it a lot. You should be able to critique that function a lot. Like, it's a stupid function. They just made it up off the top of their head. I mean, you could say a lot of things about it. You shouldn't be nice to them, Anyway, so reduce race gyration, this plot as a function of this. So then it's just, so when you have a branch, so we went through how you calculate race gyration. Like, it's this double sum, find out the center of mass, and then subtract the position of each thing, and subtract it and square it and sum those. So, and it's like the moment of inertia, except it's using density instead of, it's using like the contrast factor if you're doing X-rays or something or whatever. It is exactly the moment of inertia here because you're using the density to do it. So, but normally you'd get race gyration and scattering. So anyway, what is it? And then why is he plotting it this way? So one thing, if you have a branched molecule, there's no radius of gyration for it because, I mean, there's no end-to-end distance because it's got too many ends. So you can't tell which one to pick. The radius of gyration becomes more reasonable. And then the other thing is that when you get concentrations, so you're in dilute condition, so your structure, like a polymer or any kind of fractal thing, is floating around with a solvent in it. So it has an internal concentration that's 1 minus 3 by the molecular weight times to the 1 minus 3 by dF power, which ends up, if it's a good solvent, it's 0.8. If it's a theta solvent, it's 0.5. If it's a rod, it's 2. Right. So anyway, that concentration it carries around, so you can't make it any diluter than that. Like when you try to make it more dilute, then those things you can't dilute a thing that's glued together with covalent bonds. You'd have to rip it apart to dilute it. So you destroy it. You need to burn it to dilute it, right? So anyway, so there's this cutoff, and once you get above that concentration, it means the things would touch, and especially for these branched things, because they actually really touch. So if it's polymer coil, they can interpenetrate or entangle. But if it's a branched thing like this, they actually just touch. And if you make the concentration higher, he shows that you actually squish the things. So it goes with the volume, like the cube of the size. So as you go above C by C star, so when that's 1 and then above that, then the volume, then the thing goes with power 3, like the rate gyration goes with power -3, because it's actually compressing the volume of each of these blob things as you increase the concentration. Right, so it's kind of interesting that he saw that. That's in here somewhere. See, this plot shows that power 3 thing, I think. Figure 6. Yeah, it's not, there's a lot in this, like, right, 6 and its power -3, because you're squishing the actual 3D object. Right, if this was a fractal object and they could interpenetrate, it wouldn't be -3. Right, it is a fractal object, but they can't interpenetrate because it's branched too densely. So it goes to power 3, and the C star would be kind of here where it goes flat. Like below that, you can't dilute it anymore, so they're just floating around. They have the same size, no matter how much you dilute it, right? But that doesn't happen where this is 1. Okay, it happens way down here. So the reason for that is that this rho star, I think it's calculated for the monomers or something. This rho star, the way you calculate, it wouldn't give you where it, oh, I know why. Rho star is calculated with RG, so it's just like the mass divided by cubed. And RG, we know, is like 2.45. RG is R, the end-to-end distance for the linear chain. So the actual size of that blob is like 3 times bigger, and 3 cubed is 9. So if you divide 1 by 9, you get kind of this number, like 0.1 or something, a little bit higher. Right, so it does kind of match up. It's just RG wasn't the right number to use for phi star. Should have used like an actual R. Like he actually treats RG as if it's, see, 4/3 pi R cubed, as if it was a spherical radius, and it isn't. It's a moment of inertia. So for a fractal object, it's within the structure. The smaller is too small, and you get the wrong 1 number here. That's kind of that thing. Then that's D, and then this thing, this thing you can figure out. I showed you how to do it in the other class. So this is just right out the Flory-Huggins, and then this falls out. These axes fall out of that, and then where that equals 1. See, this is a volume. B2 would be a volume. B2 times rho, which is a number per volume, would give you like the point where kind of like a C star kind of number for B2. So B2 is the excluded volume. It's the solid volume plus the attractive interaction, which would make it smaller. Or if it's a repulsive interaction, it would make it larger. B2 includes the potential of interaction and the solid size of the thing. So it's an excluded volume, but it includes the enthalpy and the dimensions of the thing. So that's for, so molecular weight times that comes out of the Floyd-Krigbaum equation. Basically, rho times B2 would be the place we'd really expect it to be 1. That would have some meaning, and then molecular weight times that doesn't have any meaning. It isn't. So, and if it was just B2, so this is figure 8. If it didn't include the third Buell coefficient, then this would be a straight line over. This is a log-log plot, right? So it doesn't. That would be the dashed line. That's if it has just B2 flexible chain. Because it's branched, you need the third Buell. So it matches up pretty well with the branched one. So anyway, that's kind of that whole thing, I guess. Hopefully that helps. I didn't want to do that today, but anyway, is that okay? Any specific things? Let me just move on then. Hopefully it helps, This guy shows up like that. I have the controls. I can actually do a projection of this thing, I think. Maybe. This thing's locked in with the old. Oh, this is what I wanted to talk about. Okay, so this was all for a single isolated chain, right? We're getting the plot, the size of the single isolated chain as a function of temperature, right? So the theta is on the steep slope part, and then then the coil expands, and that's because this chi has a temperature dependence. So the excluded volume has a temperature dependence, and that makes this thing kind of gradually increase. So it's not a two-state solution like Palestine, whatever. It's actually a multiple state gradual solution, like reality, right? So a two-state solution. So anyway, so what happens when you go to like a polymer melt or a polymer? So this is what they'd call in the simulations like an implicit solvent. Like chi has a solvent in it, but chi is just a number. So it's as if the solvent was invisible. So you just have one number. You're talking about the interaction between the attractive interaction. So it's PP would be attractive, PS. If SS is attractive, it makes PP more attractive because it's pushing the polymer back to itself. Then minus 2 PS interactions, polymer solvent. So this chi is a net, like a net attractive interaction. So you can ignore the solvent and ignore the PS and just say PP, and is it attractive or repulsive? That's kind of what chi does. So that's in simulations, that's called an implicit solvent. Like you don't look at any real solvent. Like there's no solvent there. It's just you assume that the net effect is that it pushes the polymers together or pulls them apart. But you just have one number because those things all add up to an average energy and up with this chi, right? So anyway, so that's a single chain. But if you want to look at a mixture, actual details of like a polymer and a solvent mixing at different compositions. Also, this equation has no composition in it, right? So there's no composition. It's just the one number. It's got a temperature dependence, but no composition. So anyway, if you're going to change the composition, then you need this equation, which is the Flory-Huggins equation, which has kind of a Hildebrand, like an ideal gas mixing law in it. And then it's got this Hildebrand kind of enthalpy of interaction number. It's using the same chi, so it's the same average energy. So the same guy, this thing. Average energy, coordination number by KT, it's per monomer, or per Kuhn unit for the chain. Right, so it's that interaction. And then because they're using volume fraction here instead of mole fraction, let's see, where is this now? Here. So here in the Hildebrand approach, this is mole fraction. So this is ideal mixing of gas atoms or beads, marbles, right? So it's a mole fraction, ln mole fraction. And this kind of comes just from probability, right? So and then there's a Hildebrand interaction parameter and then the mole fractions. Here it's using volume fractions. So that means the overall volume of the system, the number of cells is fixed. When you have a fixed volume, that means it's a Hildebrand free energy, not a Gibbs free energy. Gibbs free energy has a free fixed pressure. Hildebrand has a fixed volume, right? So this whole equation, the Flory-Huggins is a Hildebrand, so you need to add PV to get the Gibbs. The difference between Gibbs and Hildebrand is a PV. Either subtract it or add it, right? So you have to add in a PV term to get the Gibbs free energy. And the Gibbs free energy is what decides miscibility. That's the thing that's used to determine the phase diagram. So you have to use this whole thing. In this case, so we'll see later, like P is actually the osmotic pressure. It's pi because it's in solution. There's no, so you're dealing with each polymer coil as if it's a floating around gas atom. It has a pressure on the solution, right? And that's P is the osmotic pressure. It's not really like an atmospheric pressure in this. In solution, right? So anyway, so that's the idea of this Flory-Huggins and how you use it. You're going to have to add in a PV to use it because Gibbs is the thing you want to look at. Because to determine a phase diagram like temperature composition, two phase in the middle, one phase outside that kind of loop, you need to say, you need to determine the critical point of this thing for one thing. So you have you have a binodal line, which is a cloud point line or the phase separation line. Then within that, you have a spinodal line, which is a point where kind of spontaneous phase separation happens within that. So it'd be within this is another curve that looks the same as the binodal, except it's sharper at the critical point, passes through the critical point. And then between that spinodal and the binodals where you have nucleation and growth, and then within it you have spontaneous spinodal decomposition. It doesn't need a nuclei to form; it just automatically forms uphill diffusion to the phase separation. And then the critical point's defined by the third derivative of the free energy. So you have a free energy expression. You can take those derivatives and you can determine the critical temperature and critical composition. You actually only need two of these. They all meet at the critical point. So you need two of these to get the critical temperature and critical composition. The only free parameters in this are composition and temperature. So if you have two equations, you can solve the two unknowns. Right, so that's the idea. So you can get that. So this is kind of experimentally what the phase diagram looks like. It's shifted towards the polymer concentration is to the left, and the solvent concentration is to the right. So Na is the polymer molecular weight, Nb is 1. It's a solvent. If it's polymer, then it's like molecular weight. All right. So anyway, so we got that. I want to mention this because we introduced Chi, so we might as well talk about how it's used. There's two ways it's used. One's in this, one's in the solution thing. I mean, where you just look at the coil size, and the other is in this Flory-Huggins approach to talk about the phase behavior. So polymer in solution, I mean, it looks kind of simple, but basically, all right, so one thing is that if you solve for the critical temperature, critical composition, they both depend on 1 over the square root of the molecular weight of the polymer. And then that means that you can write an equation in terms of both, and it means that the critical temperature is proportional to the critical composition. It's like where this is proportional to what that temperature is as you change the molecular weight. So they're going to shift to the left. So if you have infinite molecular weight, then this thing, so if n's infinity, then you just get temperatures, the theta temperature. If you have a real temperature, real molecular weight, then you're going to have this gap shows up, and this curve will shift to the left and rise up. And it rises up just as fast as it shifts to the left, because the two things are proportional. Right. So that line tells you like how this is going to, and the high end of this is just going to follow that line. So you just keep going up and up and up until the critical point reaches that at the highest molecular weight. Right, so that's kind of one nuance to it. The whole curve is dependent on the molecular weight. It's less miscible if you have a high molecular weight. Then the other nuance is this C star thing. So you have some point where you can't dilute it anymore. So what does that mean? That means that if you reach this temperature, then everything at lower composition is also going to phase separate there, including things that aren't in the two-phase region, strangely enough, because the thing carries its own composition around with it, so that you can't dilute that thing. So if it phase separates at that temperature, even though you're in a single phase region, it still has to phase separate. And how is it going to do that? The coil just has to collapse. That's the only way to do it, right? Because you have the coils. So you could separate into like oil water, but you can't, because the oil is actually a molecule and it can only collapse on itself. So it realizes it has to get out of the water, but there's nowhere to go, right? So it just collapses down. People are excited about that because that's kind of the process of like how the DNA is going to be like a meter long, right? And inside the chromosome, it's like less than a micron, like a subfraction of a micron, right? So that meter gets compressed by like 10 to the 6. And then when it's read, it partially unfolds and reads the DNA, transcription, RNA, and the proteins are kind of doing the same thing. They're folding to this like 1,000 to 1,000,000 times down to the active functional unit. People want to know like how that happens, and this is one way that it could happen, right? That you can get something that's big, like an expanded coil, and then suddenly get something that's small, right? So in this region where you're dilute enough that you can, you're in the one phase region, but basically because it's a single unit and it's got trapped solvent in it, it has to phase separate. So that region becomes this like yellow thing where you get a collapsed coil. You get coil collapse in there. If you're in this part, you get two phase, and there's a tie line that connects the two compositions that are in equilibrium. like oil water. But if you're over here, the oil doesn't come out of solution, it just collapses on itself. So you get this, a picture of this somewhere, this kind of thing. So you have good solvent, coils expanded, you have like theta solvent, so it reaches a theta state, somewhat smaller, and then you have a collapsed coil. You have like 3 states. I mean, the other option is you put charges on it, it's a rod, like a protein, polyelectrolyte. You can get a straight rod out of it. So you kind of 3, 4 conformations you could talk about. You can see that in the like in that RG plot thing. So wherever that is here. So you can see like it gets the theta state and then it collapses. So you have this other state, the collapsed coil state. You have the theta state, and then you have this gradual Flory-Krigbaum kind of expansion to the expanded coil state. Right. This is also kind of a gradual thing going on down to this. Anyway, so that's that business. What else is in here? Yeah, so we have those kind of regions in this thing. So you can say like so I cool it down, I have a 2-phase region. I get these 2 compositions if I'm within that hump, unless it's in the yellow part, then I'm basically talking about a collapsed coil. Right. And then within this region, I have a gap where you can have a theta coil. Like for real molecular weight, there's going to be a gap where you see a theta coil, Gaussian chain, R squared is L squared. And then above that kind of gap, you're going to get this expanded coil. So you can kind of map out more or less what's going on, what the possibilities are in terms of the phase diagram. All right, so there's that business. I moved this up here because I thought it belonged here, but so that's not how polymers work though, most of the time, because this term, so you can see this, all right, so this is what drives miscibility, because log of a number smaller than 1's negative, so you drop the free energy, right? Log of 0.5 it's like negative something. So this is what makes marbles mix. Like you have the red and the blue marbles, you shake them up in a bucket, they mix because of this thing, because this is a negative term, it lowers the free energy from the mix. This thing's generally positive, so that's the attractive interaction that Van der Waal put in, right? That makes the polymers attract each other and phase separate, right? So for polymers, especially a polymer blend, like N is 100,000, this term goes to 0. So you have no entropic driving force for mixing. So that's kind of a problem. In fact, so if you say you have water in a, so you have polymer that's got like, you can hydrogen bond with water. So the polymer's in solution, it can pull all those water molecules and make them stop. So the entropic change from, in this kind of thing, this entropic change just depends on how many. It doesn't matter like how big. That's key to remember. So the motion of water and how water interacts, because there's a lot of water. So even if you just have a monolayer of water associated with your molecule, right? And the water was happily floating around, and all of a sudden it's kind of glued to this thing. Or you could have multi-layers, right? Even worse. It's going to be a huge number of things because they're atoms, they're molecules, small molecules, right? So you have like 10 polymers and you're going to have like 100,000 or 1,000,000 waters. So definitely the entropy is going to be on the water side, and the polymer doesn't make any difference. Plus, polymers divided by 100,000, so that even makes it worse. Like this term is absolutely insignificant, So, but this organization of water around your molecule becomes really important, and that's not included in this kind of marble mixing thing. There's no water association and marble mixing. So people bury it into this chi parameter because there's no other hole to put it in. So it kind of collects there. So chi was originally B over T. So you add this entropy change, which is like the water organizing around the thing, right? So with the right scenario, so you have to have, in order to make it mix at all, chi has to be negative, right? Because this term, the negative term that you had isn't there, right? So you have to have like a negative chi. So, and then you have to have you have to have a negative chi. If chi is negative, then it always mixes, right? So you have to have a positive term that as the temperature drops, it gets larger, and then this is a negative term, and then you can get this UCST phase behavior. But that isn't how water works. Like water, this would be a negative term, right? It's because you're organizing the water around the polymer, so that's bad. And this is chi's an attractive term, so this would be let's see, B is negative, A is positive. If B is negative, as temperature goes up, the negative term drops out. Anyway, it's kind of hard to describe this. Basically, you need A positive, B negative, and then if you heat it up, the negative part drops out and you just have positive and it phase separates. Because positive is bad. Bad. If you increase free energy, it's bad. So it phase separates. It's basically somehow get B negative, A positive, then you get the normal situation for polymer mixing, that when you heat it up, it phase separates. I have some samples that I showed in the thermal class, but I didn't bring them. Like I can't find them, actually. I lost them someplace. I think they might be at home. I'll bring them in next time. But you can phase separate it by holding it in your hand. Like you can see that it phase separates. So we can do that next time, but I searched all over my office for it this morning, but it wasn't there. So I think I took it home. Anyway, so this is a normal phase separation for polymers, like heating it, it phase separates. So we'll look at, later on, we'll look at polyanisopropyl acrylamide, which is PINI-PAM, which people use to make like drug delivery. So you can make a gel, out of PINI-PAM and load it with drugs. And then when it reaches certain, like cancer is a higher temperature of the normal body, you can tune it to just collapse at that temperature when it heats up by this lower critical solution temperature, and then it'll dump its load there. See, a lot of drug deliveries kind of centered on PINI-PAM and like loading it with things. We'll see a paper in here that uses that. The first system that they looked at was this PVME. So it's polyethylene and it's got a methyl ether on the side. And that thing's soluble in water, but when you heat it up to 60 C or something, it phase separates out. That's the thing I have an example of that I'll bring in. But so you can see that it phase separates on heating. And you can actually, you change the composition, you can map out this curve. So if you can map out that curve, so what happens? It turns into milk. It starts out as like clear water, yellowish water, and turns into yellowish milk. And at that temperature, that's the binodal. So if you can get like 2 points on the binodal, you can predict the entire coexistence curve, entire binodal curve, and then you can also predict the entire spinodal curve and the critical point based on the Floyd-Huggins equation. It's kind of like basically you just need 2 points on this and you can get this whole equation. And you can predict the entire phase behavior of the system, and it works really well. Like it works almost perfectly well. There's a few nuances, but basically it's incredible how well that thing works to predict polymer phase behavior. You have to put in like a 2-parameter chi to do this, but you just say 8, you have 1, 2 parameters, and that's it. Because you're controlling temperature, you're controlling the, the molecular weights, controlling the composition. So you can just 2 measurements, you can get this curve. So anyway, and it's easy to do. Just look at it. You get cloudy. That's it. So it makes a pretty simple analysis for phase behavior. That's why it's popular, like Floyd-Huggins equation. And it works for solution. For solution, you make MB1, right? So, and then what else is in here? It's like a bag of tricks here. All right, so this is a different subject. All right, so I jumped off onto the chi thing. Any questions on this? Or, it's kind of like the standard thing for polymer phase behavior. So I was at this point, right? So this is, and also I mentioned this overlap concentration, because that's the point here. So we have like the thing carries around a concentration with it. If it's branched or if it's linear, it's got solvent in it. It's a fixed composition. It's the size of the thing, and then the mass gives you this kind of density, which is a C star number. So you talk about above and below C star. defines where the coils overlap. Like C star equals, well, concentration equals C star, you're where the coils touch each other. And this is, if you put in like size, mass is size to the df, and then size cubed, you get df minus 3. And if you want that in terms of mass instead of size, you get n to the 1 minus 3 over df for that. And that will give you, so you have different molecular weight of the thing you're looking at, and then you plot the C star number, you can get this. I mean, you know the fractal dimensions, either 5/3, 2, or 1 for a rod. Right, so this power is going to end up being 0.5 for theta, 0.8, minus 0.5, minus 0.8 for a good solvent, and minus 2 for a rod. Because for a rod, df is 1, that's 1 minus 3 is 2, minus 2. Right, so those are the. So there's another way that people had to measure the C star, right? So measure the specific viscosity. So this is I don't have what that is here, so I should say so if you're talking about solution viscosity, so you can take a usually it's done with a bobbing cup, so it's called a Couette viscometer. So this has like a torque meter, and then this is in a cup. You put your stuff in there, that coming out, right? You spin it around, and you can get the viscosity, the solution, right? So if you plot that, like that viscosity versus concentration, then you find out that it drops pretty good, and then it kind of plateaus out at the solvent viscosity. And there's a small difference, but you can't see it. In other words, the solvent itself that it's in, so you have polymers in a solvent, has a viscosity, and that washes out any signal you have down at the low end. So you got at first you have to go like the viscosity minus the solvent viscosity, and then people will normalize that by the solvent viscosity, and that's a specific viscosity. And then you can take that number, so that's a unitless number. And you can take that number and take the concentration to 0, like the limit, this concentration goes to 0, that would be like the intrinsic viscosity. So that's just a number, there's no units. But that number is going to be this mark point HOUWINK equation. So that's Herman Mark from Brooklyn Polytech in like 1960. The point, I don't know who that is, M to the A. This is basically like this intrinsic viscosity. We'll go through this later, but this A is basically like our 0.8, 0.5, 2 number. Right, so we'll go through why that is, but basically that's the measurement you're talking about. So you're going to plot the specific viscosity. You're not going to plot the viscosity because the viscosity will wash out. If you subtract the solvent viscosity, then you can see that this goes to power 1, and this goes to something like a power of 3 here. There's a cutoff point. So over here, the chains are isolated. Here they entangle. And this 3 comes because they're entangled. So this thing was originally called C star. Same thing as like the coil, the mass per volume of the coil. Right? But now they found out that isn't exactly true. So this is called C entanglement. Okay, so I want to show you like how this works. So this is a paper by Colby from Colby's at Penn State. He's done a lot of this stuff. So you see the specific. So this is the viscosity minus the solvent divided by solvent. So when this is 1, it's specific is just the viscosity minus the solvent. And the other one's the viscosity, the specific, and the reduced. When you divide it by the solvent, it's a reduced viscosity. And then when you take the limit to concentration 0, that's the intrinsic viscosity. Just the names are confusing for me, but you can get the same thing from the diffusion coefficient, the cutoff point, basically the steeper power. So that's your entanglement concentration, originally called the C star. this is the same paper by Colby. So he measures this for polyelectrolyte, but the slope should be 2, right? Because the rod. He measures the stars are the polyelectrolyte C star measured by scattering, I guess. And then those circles are measured by viscosity, this entanglement, and they're quite a bit different. Like they actually follow the 0.8 law, the good solvent law. And then these two are like polystyrene and toluene or something. Like he says what they are, but basically red stars are C star, so they follow this 0.8 for a good solvent. The 1 minus df 3 by df gives 0.8, and then the red circles are CE, so that entanglement matches pretty well with this. In other words, they follow the same trend in molecular weight, this 0.8. So in other words, he's measuring that by doing a concentration series and finding where that thing cuts off. So he has some explanation for why that happens. So it can be the same, so C star can be kind of like C entanglement, or they can be quite a bit different because the rigid rods. All right, so what he says in this paper is that they're measuring different size scales of phenomenon. So the viscosity is a bulk measurement. The raised gyration is a local measurement, like on a nanoscale. Viscosity, this gap distance in that Couette viscometer is like maybe like 3 millimeters or something, or a millimeter in that range. So basically, it's much larger. It's 10,000 times bigger than the raised gyration. So because of that, he's saying you're actually doing a bulk measurement, and these rod things hook up into a network, which is a good solvent network. Colby has a way of making things into a long story. You can see this is 25, so it's a 20-page paper. But he's not short in words, but he is pretty bright, So yeah, a 20-page paper to kind of say that. I mean, he's got the measurements in it and all, but it's a little bit of a flimsy argument in a sense, but basically he's got the measurement to back it up, and it has to be explained somehow, and his explanation sounds as good as anything. So basically the two things are 2 different size scales, and because the rods at large scales can make a self-avoiding walk, like they can hook together somehow, like this sketch here, then that can be a good solvent for the blue circles. And then when it gets closer to get the actual raised gyration of the structure and calculate C star, it follows the rod structure. It's a little bit of a hand waving. It's true you're comparing a bulk measurement to a nanoscale measurement, and there's differences with size scale. But whatever. So anyway, that's one of the nuances of this business about C star. The other nuance is it's something that Colby's turned into like a little industry, and kind of, I'm not sure there's that many people following it, but he's published a lot of papers in this subject, like how CE and C star aren't the same. Also, some of the prominent rheologists and polymers have kind of drawn attention to this idea that this entanglement concentration and the C star aren't the same number. So the guy at Princeton, so the other thing that people are looking at a lot of is this extensional viscosity, extensional flow. So basically this is I was looking at this last night, and it's like, I didn't know what a shadow graph was. I didn't remember, but you can Google that. Shadow graph is like when they show a gun, like a gun, and you can see the cloud of the smoke going from where the barrel. So what it is actually shine a bright light at the gun, shoot the gun, have a high-speed photograph of the shadow of it. You have like a screen behind, because you can't see that. Like if you ever see a gun, you don't see a billowing cloud around it, right? So basically it's because they're taking a picture of a shadow of the thing, and the density changes in it are enhanced in the shadow somehow. I'm not sure how. There's a large explanation for why, but basically these are shadow graphs of flow, of polymer flow, and extensional flow. So showing how the little capillary, how the filament breaks apart, like eventually it forms beads. Right, so a lot of people are interested because if you make fibers, you have to go through extensional flow. You have to draw it out. So you extrude it through a die, and then it swells because of the normal forces. Then you have a spinneret that's pulling on it. So you're kind of pulling it like if you're taking chewing gum and stretching it out. Like when you're a kid, maybe you did this, but so that's extensional flow when you do that. And when you do that with chewing gum, you find out pretty quickly you can only do that to a certain extent, and then it flops over and there's a gooey mess all over you. You've done it. Okay. I've done it too. And I don't remember when, but I have a very firm grip on how this works. If you try to stretch it, you think, oh, this is no problem. It's really easy. And then all of a sudden it just stops and it just droops down and it's just all over everything. I don't recommend trying it, but basically, I'm not proud of it. But anyway, so the problem with it is this. If you want to get a constant, this should be gamma dot or gamma prime. So the derivative of the strain rate, d gamma d time, should have written that out. So the same thing as dv dz, dvz dc. So you're pulling it, it's a tensile. So you're changing the force x in the x direction, and you're looking at the change in length x in the x direction. So the strain is dx over x, right? Dx over dx. So anyway, so dvz dz, that's this extensional strain rate. So if you take the integral of that, you find that, or it is this equals a constant. So if you take the derivative of this, you find that vz has to equal z times a constant, right? The integral of that thing. Then you have dz dt, which is vz. And then you're going to have dz by z is constant. The integral of that is log. So you end up with z is exponential. So if you want to have a constant strain rate and extension, you have to exponentially increase the length. So you'd have to, so say you start out walking, then by the end of the room, you got to be like 60 miles an hour. But you got to just keep going faster and faster and faster, right? Which isn't really experimentally possible. So people do this, they don't do that measurement because it can't be done. And then when you're drawing a fiber, you can't exactly do it, but so they have like some kind of flow set up like this. So you go in and then out. And then right here, right in the middle, you have perfect uniform like strain rate, XX is constant. So you have some kind of weird flow cell to do this. And then if you're doing a polymer melt, you can't do that. So they do other things to get constant extensional viscosity, right? So it turns out if it's a Newtonian fluid, the extensional viscosity is proportional to the viscosity, the normal shear viscosity, and it's 3 times it. If you're in a polymer fluid and you change on the constant, say it's in the solution, you change the concentration, you get kind of that exponential behavior, that knee thing, and then some concentration, you get that the thing draws out, right? So anyway, it's when the thing's flowing and you're deforming the molecules, the overlap changes. That's the theme of this thing. So if it's an unperturbed chain, it's got 1 C star. If the chains are stretched out, the C star drops significantly. You can get a point where they entangle. So this is McCosco at Minnesota. He's like the father of Minnesota chemical engineering, which is a top program in the country, right? But he's a polymer guy. And so anyway, he studied this quite a bit. So there's a lot of people studying extensional viscosity, like for various, just to kind of say what's going on with the molecules. And the overlap happens a lot earlier when you're doing this extensional flow than when it's just a quiescent, just sitting there. So this is a standard shear flow, and then this is the extensional flow. So you get a different relaxation time in that exponential function here. So anyway, we might have something like that for the homework this week, but then yeah, so next time I'll go to this coil collapse stuff, but anyway, hopefully that's all right. I just wanted to mention those things because they're topics. There's a lot of papers on all those topics. Extensional flow this year, maybe there'll be like a couple hundred papers. Like a lot of people, the rheologists are all looking at extensional flow. And then this business, this is mostly Colby and friends talking about it, but he's made it popular. So I think this stuff, the business of the difference in the C star CE. And this thing's older. This is kind of from the 1990s, I guess. This business of the phase diagram. And this is really old, but it's still popular, like the phase separation, the LCSD. That's it. So let me quit there. Any questions or anything? Good to be back live, you know. I don't know, it's good to kind of show up, but hopefully it'll be okay here. Anyway, so thanks for coming. Yeah. Oh yeah, we got 5 people over there. So 5 people are missing. Yes, I can hear you. All right.